All right, so our next speaker is Nathaniel Putzig from the Planetary Science Institute. Fan, you're welcome to the Mission to Mars summer program for high schoolers. We'd love to hear what you have to say today.
Okay, great. All right, let me see if I can share some slides here. How's that look?
Yep, that looks great.
All right, so yes, I'm Nathaniel Putzig. I'm a senior scientist at the Planetary Science Institute in our office in Lakewood, Colorado. I'm one of my roles as a planetary scientist is as the U.S. team lead for the shallow radar instrument on the Mars Reconnaissance Orbiter. And I spend much of my time working with radar data. And one of the things we do with radar data is map ice on Mars, both at the surface and in the subsurface. Of course, we don't do everything just with radar. And what I'm going to present to you today is this project called SWIM, Subsurface Water Ice Mapping, which we've been conducting over the last several years with a goal of characterizing ice deposits on Mars as a potential in situ resource for future human missions. This is a project, NASA-funded project, which is arranged through a subcontract with the Jet Propulsion Laboratory. So over the several years, we've had quite a large team of folks working on this project. It's led by a couple of us at PSI, myself and Gareth Morgan. And then we have a bunch of folks from various different institutions that are working on different aspects of the study. There are elements of using imagery and elevation data to understand geomorphology, using thermal and neutron spectrometers to understand ice presence, of course, the radar data, and then there's some other activities involved trying to amalgamate the different data sets. So just to give you an overview here, of course, this isn't completely new, this understanding of ice being on Mars. There are multiple lines of evidence that have been accumulating over the last many decades, really, that support there being subsurface ice off of the polar caps across the mid-latitudes of Mars. So I mentioned the neutron spectrometer data. This is essentially a hydrogen detector that shows strong indications of ice in the higher mid-latitudes. In addition, thermal measurements, essentially temperature at the surface, can be used to understand the possibility of there being a buried ice table. And again, this seems to be good evidence for ice in the upper mid-latitudes, poleward of approximately 50 degrees or so. Both the neutron and the thermal spectrometers have a sensing depth within the upper meter or so of the subsurface. So if there's deeper ice, they're not really going to detect it very well. Another method of detecting ice is through imagery. Of course, there's a somewhat direct detection of ice if a new impact occurs and exposes ice at the surface. This has happened many times over the course of our mission, the Mars Reconnaissance Orbiter. And the high resolution imager, HiRISE, on that spacecraft, along with the context camera, have been able to identify a number of these recent impacts. You can actually see the ice sort of sublimate away over time. And there's also been some spectral indications that this truly is water ice. In addition, imagery can be used to understand geomorphic forms that may be consistent with ice, such as these lobate debris aprons around this this mountain in the image on the far right. And the radar instrument, it's a radar sounder, shallow radar, has actually detected the base of these ices and given us good evidence that they are in fact very ice rich. However, most of the prior studies that kind of fed into these findings focused either on an isolated region or they really focused in on single data sets. What's new and unique about the SWIM project is that we're really integrating a full suite of these different data sets to map ice broadly across Mars. And the other unique aspect of it is the motivation of in situ resources. The real push here is to identify where this ice is, where it might be accessible for astronauts on future human missions. In addition to, just feeding into the mission planning, it is also helping us to understand how to go about doing a better job of mapping this ice. The radar and the other instruments really were not designed specifically to look for shallow buried ice on Mars. They had other goals in mind when they were designed and implemented. So this use is a little bit beyond what they were designed for, and there's kind of a bit of a blind spot that I'll talk a little bit more about. So this work is also informing what we should do next to do a better job of assessing this buried water ice. So the technique that we use includes data from 3 different orbiters at Mars. And as I mentioned, neutron and thermal spectrometers from these instruments listed here, geomorphology from the imagery, and then the radar data from the shallow radar on MRO. In the radar data, we kind of divide up into 2 aspects. One is the radar reflections that come directly off the surface or very near surface. And then the discrete radar returns that come off of interfaces in the subsurface. I mentioned the base of the ices and the glacial ices. So for each of these techniques, we isolate some distinct property that provides a proxy for whether ice is actually present or not. We then term this ice consistency for that particular technique. And we set it to range between -1, which means wholly inconsistent with the presence of ice, and +1, which means wholly consistent with the presence of ice. So 0 means that that data set or technique is not saying whether there is or is not ice. So this work has been carried out in several different phases, roughly corresponding to calendar years 2019, 20, and 21. The work that began in 21 was in the fall, and we're just finishing that up this summer. So I'll be showing you a lot of the results from the first 2 swim seasons, if you will. So the neutron spectrometer data has been used in the past to map out what's called water equivalent hydrogen. And this is modeled in a 2-layer sense. There's a dry layer at the surface, and then the hydrated or icy layer below that. So the prior work by Putzig et al. Mapped out this water equivalent hydrogen all across Mars, and the higher values, of course, are consistent with water ice. Once you get well above 10%, approaching 20% or more of water equivalent hydrogen, you can be pretty sure that it's going to be water ice and not just a like say hydrated minerals. So this map then we convert to this consistency measure by essentially mapping the water equivalent hydrogen values to the consistency numbers, which are presented here in a scale that runs from red to blue, where red is things that are inconsistent with the presence of ice, and blue are things that are consistent with the presence of ice. And the deeper shade of blue indicates a larger, more confident consistency with that ice. So we do this for each of the various data sets. In some instances, there are multiple measures that go into it, such as this thermal layer. We use TESS, that's the thermal emission spectrometer that ran on the Mars Global Surveyor. We use data that models thermal behavior, what we call thermal inertia. And when the layered model shows a consistency with the presence of buried ice, then we get a higher consistency value. In this instance, we don't actually map out the inconsistent values, and so all the shades here are in blue, and the brighter shades of blue then are progressively more consistent with the presence of that ice. I mentioned the radar surface return effect. Essentially what we're doing is we're calculating the surface power from the radar relative to what a kind of an average power would be, where the power that comes back from the surface is low. That's an indication of lower density materials within kind of the sensing depth of the surface return, which is about 5 meters depth. So if there's low density, then that is a measure that is consistent with the presence of ice, since ice is of lower density than Martian regolith. And so we then assign consistency values based on how the power varies relative to the global average. So these sigma values on the right are the relative power. So this is somewhat patchy. One of the issues with this data set is you get some false positives for ice. For example, if you have a thick layer of low density material like dust, say, that could show up as a consistency with water ice, when in fact it's just a very low density material blanketing the surface. The next layer up here is the geomorphology layer. This one's a little bit different in that it isn't just kind of computed from geophysical data sets. This involves a lot of human effort to go through and look at images in great detail and tally up landforms that appear to be consistent with the presence of ice. So we identified 8 different landforms that we believe have some consistency with ice, and we essentially go through all the imagery and count these up. In this instance, we use a CTX, that's the context camera on the Mars Reconnaissance Orbiter, that has a resolution of about 6 meters per pixel. We use these images to go through and map out where these features are across these all of the mid-latitudes of Mars. The first phase of this work in 2019 was a little bit rushed, having to do with a government shutdown that occurred in the midst of our project. So you can see the coarseness of these like 10-degree boxes. We weren't able to go down to the finer and finer resolutions in that first phase of work, and mostly the northern hemisphere here. But when we came back in 2020 to include the southern hemisphere, we were able to get down to finer and finer resolutions, down to 1 degree in these transitional zones from where the ice features are everywhere to where they sort of peter out. So the new work that is ongoing is going back and looking at this 2019 zone again to do finer resolution work. So that's this map basically shows where we're going back in and doing additional work. In this case, we're in addition to doing the finer resolution work with the CTX imagery, we're actually wrapping in some high-rise imagery, which goes down to 30 centimeters per pixel, and adding in another feature, a mapping of another feature, what we call polygonal terrains. And these polygonal terrains have been associated with those ice exposing impacts. So we kind of use them as a proxy for areas of higher confidence of near surface ice. So we're folding that high-rise imagery analysis in with the CTX work, and the CTX work is then also being expanded to finer resolutions, especially in these zones of great interest that are closer to the equator. I mentioned the radar surface power, but in addition, we get discrete reflections off of interfaces in the subsurface. And sometimes we can make a measure of the radar properties, what we call the dielectric constant. And if that is of a certain lower value towards the 3 end of the spectrum here of dielectric values, then that becomes increasingly consistent with the presence of ice. So where we're able to get these subsurface discrete reflections and able to assign a dielectric value, then we map that out as very high consistency with ice. This shows up in a much more patchy sense. We don't get these returns everywhere across the planet. They tend to be in isolated areas. Some of these big patches in the north are believed to be very ground ices that have extents across the plains. You can see some of these other finer features in here. These are actually associated with those debris-covered glaciers that we had that image of in the earlier slide. There are actually a number of these detections in the south. They don't show up very well on this global map. So we'll zoom in here on one area in eastern Hellas. Hellas is this big basin in the lower right of this global map. So we're going to zoom in on this area right here. And this shows some of these debris-covered glaciers, also known as lobate debris aprons, LDAs. And where we get these subsurface discrete reflections off their bases. And that allows us to constrain the presence of that ice. So anyway, taking all of these data sets together, then having assigned consistency values, one may then take a more holistic look at how all the data sets are informing the presence of ice. So one means of doing that is to simply average together the consistencies measured from the different techniques. So here, this little equation just is an averaging of the ice consistency from the neutron spectrometers data, the thermal spectrometer data, the radar surface return, the geomorphology, and the radar deep or dielectric measure from the discrete reflectors at depth. So you just add all those up and divide by the number of inputs, and that gives you kind of an average look at ice consistency across all these regions. So in this map view showing the result from that equation, we overlay red X's here, crosses, showing where some of those ice exposing impacts occur. And we were happy to see that the occurrences of the ice exposing impacts more or less line up quite well with where we're finding very high ice consistency across these different data sets. By and large, the red crosses always occur in a blue pixel. They're in varying shades of blue. But this does lend us some confidence that what we're doing with the remote sensing data sets actually does map to where the ice is in the near surface. There are, however, alternative ways of amalgamating these different data sets. Once we have all of the data sets, one thing I kind of alluded to earlier is that each data set has a kind of a different sensing depth. So one can then kind of put the different data sets together in a different fashion to look at different depth zones. So for instance, I mentioned that the neutron and thermal spectrometers have a 1 meter sensing depth. So we can set a depth zone of 1 meter, and then we can adjust our equation to include things that give us information about that depth zone. So in this case, we just take the neutron and thermal spectrometer data directly as they give us information specifically about that depth zone. And then we take these other couple of data sets, the radar surface return and the geomorphic, kind of a shallow subset of the geomorphic measures. And we weight them down a little bit because they have deeper sensing depths and only partially inform that 0 to 1 meter zone. So then we have this sort of weighted equation to get us towards ice consistency in this 0 to 1 meter depth. So that's what this map is. And I'll toggle back to the prior map so you can see how that changes between these two approaches. So yeah, you can see there's a kind of a stronger gradient toward the higher latitudes, and that's kind of expected because the ice becomes the top of that ice is expected to be deeper and deeper as you go to lower and lower latitudes. And this result is very consistent with that expectation. So you can do the same for other depth zones. So here's another map using now zeroing in on a depth zone of 1 to 5 meters depths. In this case, the spectrometer data drops out of the equation entirely because it doesn't give us information from below 1 meter. However, we still have the radar surface return that senses down to about 5 meters, and the shallow geomorphic term, as well as now that radar deep, the discrete reflectors from below pass through that zone and give us some significant information about it. So that one's weighted down a bit because the real sensing depth there is more on the order of tens of meters. But nevertheless, you now have a kind of a different measure for this somewhat deeper ice. And finally, we can do the same sort of analysis using the deepest of the methods. And this is essentially an average of the result from the deeper radar term and the geomorphic terms that identify ice at greater depths. So this, doesn't show as much variation across it because we're effectively just using 2 of our different techniques in doing this mapping. Anyway, so the one nice thing about this is you can kind of use these terms and set up your own equations if you so like to kind of put these things together in different ways. So for example, we can take those 3 depth zone maps and then average them together and give us this sort of overview of ice consistency across all depth zones, but with these weightings applied. So then this gives us kind of a somewhat more nuanced look at where the ice consistency is highest, the deepest blue is where we have indicators of ice across all three of these depth zones. And where the shades get lighter, then maybe you're limited to one or two of these depth zones producing a signal of ice presence. Again, there are many different ways to kind of put this together. Instead of averaging them like that, we can just overlay them. So this is an overlay where each zone has a different color assigned to it. And then you kind of stack them here, and you can kind of more easily see where the different depth zones are informing that presence or absence of ice. So just a quick summary of the ongoing work. This latest phase of swim work is really focusing in on the geomorphic mapping, because as I mentioned earlier, we were limited in our ability to go to finer resolutions in the earlier phases, and we were finding that the geomorphology is really kind of the key to bridging the gap between the radar sensing depths and the thermal and neutron spectrometer sensing depths. So the latter go to about 1 meter, and the radar doesn't really kick in until well below 5 meters, really more like 10 or 15. So we want to do the best we can with the available geomorphic data. And the first part of this extended work really is going back and looking at that CTX data in much finer detail, mapping out those paraglacial features at finer resolution when we get closer to the equator. And that we bias it towards closer to the equator because those are the more desirable places to send humans. The further you get from the equator, the more and more difficult the thermal conditions are over the course of the year, and it becomes much more of a challenge to sustain a human presence at the surface over the course of a mission. And the second aspect of this extension has to do with folding in these high-rise surveys. Of course, high-rise coverage is relatively sparse. It's only a few % of the surface that actually has high-rise imagery. But nevertheless, we found this association of these thermal contraction polygons with the ice exposing impacts. So we really wanted to fold that into the study. And we've been mapping these features out across these same latitude bands to get a real sense of where that higher confidence ice is present. So these are, these red outlined areas are the ones that we're doing the CTX mapping updates. These are some of the paraglacial features that are being mapped. They're, essentially I mentioned 8 landforms. We actually mapped 9 landforms, but this last one here in the lower left that we call fill, essentially it's fill in craters or other low-lying areas. It's similar to other crater fill materials, what's often referred to as concentric crater fill, which is related to these glacial landforms, but it doesn't have the kind of glacial character to it. So there's not a high confidence level that it's associated with ice. It could be filled with non-icy materials. So while we're mapping these, we're not actually folding them into the ice consistency terms. This then just shows the updates. This is a little bit out of date as far as the current extent of progress. And we've actually got essentially all of these boxes done now, and we're just finishing up the the last of the mapping before these new products will be released. So let's see. So yeah, this is just an example of one of these ice exposing impacts that also shows these polygonal features to give you a sense of what it is we're chasing after with the high-rise mapping work. Anyway, just a few more details here on the nature of that mapping and the focus in on what we're kind of calling the ice line, where the paraglacial features sort of peter out as you go towards the equator. And then an example of some of the different polygons that are being mapped as part of this project. So you see there's a lot of variation in the nature of these polygons. And then a zone just showing where the high resolution geomorphic mapping is being done. And then finally, just a little summary here. These products have been coming out of these phases are being made available to the general public through our website, swim.psi.edu. They're being used, as I said, to help inform planning for future human missions, as well as planning for new instruments to go and do a better job of mapping this ice. The work that's coming out of the project is being published. We have a paper out in Nature Astronomy from 2021, and there's another book chapter coming out very soon now. Basically all the work's about done on getting this book together. They're just finalizing some of the permissions, I guess. So that should be out in the coming month or two. And the products, including a lot of the different layers that I talked about, are all available on this website. So you can pull them down yourself and play around with them to your heart's content. So I'll stop there, and I'm happy to take questions depending on what kind of time we have.
Yeah, thank you so much, Stan, for your lecture. You know, one of the things our students are going to be needing to do for this course is pick a landing site, decide where they want their mission to be. I think the work you're doing here is going to be really helpful for them to find places where there's ice nearby. And
Sure.
like you said, you know, the sort of farther away from the equator you go on either direction, the harder it is to land a human mission. Yeah. So based on what you know so far of all the research you've done, what are some of the great landing sites that you think would be useful to use for students?
Right. So there's been an awful lot of interest in some of these ground ice terrains, notably in Utopia Planitia and in Arcadia Planitia. And you know, I think there's pretty good indications that we have buried ice there. You know, the swim results, most, if not all, of data sets point to the presence of that ice within, you know, the upper few meters of the surface. So it should be accessible. One concern, though, is that we're finding that the indications of excess ice, where, you know, ice is sort of dominating the volume in the subsurface, are not as strong as initially suggested by the first papers, like the Bramson et al. 2015 and the Sturman et al. 2016 papers that describe the radar results at those sites. So we think there may be more admixture of regolith and dirt and dust in that ice, which could impact the ability to process it depending on what, you know, techniques are being used to extract it. So if one really desperately needs to have very pure ice, probably a more certain bet is to aim for the debris covered glaciers. Now they're more geographically isolated than these broad expanses of ground ices. But one thing that is coming out of this swim mapping, and I think has been documented elsewhere, is there are actually areas where you have both this ground ice and, at least nearby, these buried glaciers. So ideally, what I would aim for is have a site where, you know, you can land on a nice flat area that's safe to land on, not a lot of rocks. And then you're pick one that's within striking distance of one of these glacial features. You know, the glacial features tend to be much more rocky, rougher surfaces. And you know, a lot of the people looking at landing sites are shy away from them because of that. But you know, if you need a big block of ice to extract resources from, you might want to be close to one. And if you can have the ground ice right there under the landing site as well, then you're kind of got the best of both worlds. So that's the direction I would go.
Yeah, I definitely think that's good advice, and it just kind of illustrates the challenge that of students, you're gonna have to balance like having great resources available versus safety for the crew to land and operate at. Those are the two sort of things you'll need to juggle. All right, question from Heliosa. You say there's a couple of smaller spots closer to the equator. Would you say they are a reliable source of water or possibly drinking? Like how much processing would you need to do on some of these water deposits to get them useful for humans?
Yeah, so I think I wouldn't put a whole lot of credence in the isolated spots closer to the equator that are removed from the sort of overall, you know, ice line, if you will, on the more, you know, regional sense. You know, there are, as I mentioned, a number of potential false positives. So for instance, the radar surface return, low density is really all you're measuring. The neutron spectrometer, you're measuring hydrogen. And, you know, in areas where these two kind of come together, you could have, you know, hydrated minerals that are in a low density deposit, and this might show as a high ice consistency, but in reality, it may not actually be. You know, there are certainly ways to extract, you know, water from hydrated minerals, but again, that's another ball game, and you've got to bring a different set of equipment if you're going to go after that. And if you really are going after hydrated minerals, I wouldn't use our maps for that. You want to use hydrated mineral mapping. There's a whole other team that's been working kind of in parallel with us, chasing after where the hydrated minerals are. One difficulty for them, though, is they can't really extrapolate to depth very well because there's not a good way to measure hydrated minerals at depth. You can measure them at the surface with spectrometer, but you don't really get much sensing depth. Not even a meter. It's really within the upper centimeters.
Question from Carl. He says, hi, I understood the essence of the ice consistency maps, but I'm curious about the areas consistently colored in black. What do they exactly correspond to in the Martian surface? Are they related to elevation?
Right, sorry, yeah, I should have pointed that out. Yeah, so we blacked out elevations above 1 kilometer above the Martian datum. And that was basically, we were told to do that because, you know, that elevation is extremely difficult to land, you know, a human mission on, and it's very unlikely that at least any of the first human missions would go to those elevations. So it was solely a choice based on mission scenarios. Really, they're thinking mostly below 0, maybe even below like -1. But to be conservative, we set the elevation cutoff at +1 kilometers. So yeah, there very well could be lots of ice consistency at those higher elevations, but we did not map it.
Okay, great. Any other questions, students? Feel free to raise your hand and I can recognize you. You can even ask Dan by voice if you have a question. So Dan, you mentioned those maps are available on the LPI website. It's pretty easy for students to just download them, or they use regular images, or do they need any special tools to look at those?
It's not the LPI, it's PSI. So
Oh, sorry, PSI, sorry about that.
So I just put the URL in the chat. Yeah, I think you should be able to figure it out from the information that's on the website. You know, any GIS tool should be able to read the maps. Of course, we use ArcGIS a lot, but there's like open source GIS tools that should also be able to read them. And there's also just like imagery of some of the maps that I showed, that just, you know, PNGs, I think they are. And you know, if you have problems, please don't hesitate to get in touch, and we can help you decipher, you know, whatever you need.